Finding for number 7, the cable tension. mg down, tension up. Tension's winning because it says it's accelerating upwards. It even gave me the acceleration. Yeah, I would say winner minus loser equals MA. How would I get the tension by itself? In fact, I'm going to cheat and go like this. There. The tension is going to be, because I don't have much room and I don't want to recopy this question, mass times 9.8 plus mass times, what did it say the acceleration was? 1.3. Is that right, Mr. Duick? Oh, I put times instead of add. I was going, that seems way too big. Thank you. So that gives me a cable tension. Find the speed after 30 meters. So here I would let D equal 30. I would let VI equal 0. A equals 1.3. And I can find V final. Okay? Then, see, there's 2 ways you can find the work done. The first way you can find the work done is to go force times distance. What is the applied force? I think the applied force is tension. I think if you go tension times a distance of 30, you'll get 266,400 or 266 kilojoules. Now there's a second way you could have done this, and this is all this question is really asking you to realize, is that the second definition of work is change in potential, change in kinetic, except both of the initials are 0, so you could say how much work was also done. It's going to be potential energy final plus kinetic energy final. It's going to be MGH, 800 times 9.8 times 30, plus a half M. Whatever answer you got for V final here, squared. They said 8.83. And lo and behold, I didn't get the same answer. What did I do wrong? I put an 80 instead of an 800, Mr. Duick. Let's try that again. And lo and behold, I also get the 266,000 or the 266 kilojoules. So how do I find work? Force times distance, or change in potential plus change in kinetic, or the area under a graph, but there's no graph here. Is that okay? That's a real quick explanation. Any others? So today we're going to finish off the unit. Today we're going to end the lesson with some fairly nasty Physics 12E stuff. And I'm going to give you a take-home quiz. Monday, no school. Wednesday, we'll be going over the take-home quiz. Friday is your test. I guess that means I'll probably do a tutorial when? Either Wednesday or Thursday after school, but I got to double check to see if I have a meeting on Thursday. So, lesson 3, power. Power. We use the word power in a variety of ways in everyday language. But in physics, power has a specific meaning. Power is how fast you're doing work. Power is the rate at which work is done, or the rate at which energy is transformed from one form to another. It is a scalar. In fact, pretty much everything this unit is a scalar. Work, energy, time, speed, scalar. Power, scalar. Anytime I tell you that something is the rate at which something is done, that usually means there's a time underneath it. For example, velocity is the rate at which distance is changing. It's distance over time. Acceleration is the rate at which velocity is changing. It's velocity over time. It's meters per second, which we wrote as meters per second squared. Power is work over time. The unit for power, well, I guess it would be a joule per second. But we've given that unit a special name. Does anybody remember what we measure power in? What? 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 Yeah, I'll never get tired of that joke. symbol W. Named after a scientist whose last name was? What? Yeah. Okay. James Watt. He didn't invent the steam engine, but he really, really improved it quite a bit so that it became economically feasible to put them in factories. He was one of the big people who helped bring in the Industrial Revolution. Also a heck of an advertiser. I'll tell you why in a little bit. It says a 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What is her power output in watts? Okay. Power is work over time. That formula is on your formula sheet. If you're going up a flight of stairs, what force are you, because work is force times distance, which force are you working against when you go upstairs? Gravity. In fact, really, the amount of work or the amount of energy that she's changing, she's gaining gravitational potential energy. It's coming from the food that she ate. Divided by time. Her mass, it says, is 60. 9.8. A height of 3.32, a time of 2.6 seconds. How many watts of power is this girl generating, is this girl creating? What'd you get? Jason? 751 watts. Jason? What would happen if she ran the stairs faster, if time got smaller? Okay, if you run stairs faster, how do you feel? Okay, when we talk about tiredness, we shouldn't use the word work. When you say I'm working hard, really we should say I'm powering hard. Power is what makes you tired, Sydney. Work isn't what makes you tired. It's how fast you do the work that makes you tired. You run the stairs faster, you're going to get more tired. Oh, you make the stairs shallower so that maybe it takes you 20 seconds to walk up the stairs. Maybe like the stairs in the back field that are a little bit shallower. Oh, you know what? It's not as tiring. It's not as tiring. You still burn the same amount of energy. Oh, Jason, what if the mass got bigger? How would this person feel? Would they use more power or less power? If this mass got bigger, would they be generating more power or less power? More? Would they feel more tired or less tired? This is why little kids can run around like crazy and we can't. I don't know if you ever wondered. This is the physics reason why little kids seem to have just so much energy. They got a way smaller mass. Now, they do take in less food, but it's not proportionally less food. They got energy and to burn. Oh, that explains it, yeah. Oh, this is also why for heavier people, exercise is such a challenge. Okay. I said James Watt was a great advertiser. First of all, 1 horsepower. We can also measure power in horsepower. We measure motors in horsepower. That's the imperial unit. 1 horsepower is about 750 watts. So this girl's power output is approximately 1 horsepower. James Watt, very good advertiser. You see, he was improving these steam engines 200 years ago, and he was trying to convince factory owners and farmers to buy them, and they said, well, what would I use this for? And so he brilliantly invented a new unit. He said, oh, this motor will replace 5 horses. It has 5 horsepower. And the factory person would say, oh, I can exactly now figure out how much I can get out of that motor. How good an advertising gimmick was it? How good a unit was it? Do we have horses in our everyday lives right now? A few of you do, apparently. Most of you don't. But how do we measure engines still? Horsepower. We still use this unit, even though if I said how much work or how much power can 750 horses generate? No idea. But we still talk about a 750 horsepower motor or a 100 horsepower motor. So good advertising. Since motors are measured in horsepower traditionally, although most electric motors now are measured in watts, let's do a horsepower question. If I give you horsepower on the test, I will tell you that 1 horsepower is 750 watts. You won't have to memorize the conversion factor. Anyways, example 2, how long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? What's this question asking us to find, Alicia? Time. And I see horsepower. Hey, you know what? We have an equation that has power and time in it. This one. Power equals work over time. Let's get the T by itself. Oh, I think I can kind of cross multiply. Stuff moves diagonally. It's really P over 1. I think time is going to be the work divided by the power. How much power? 5 what? Okay, we don't use horsepower. What's 1 horsepower the same as? Okay, so it's going to be 5 times 750 watts. How much work? Oh, we're lifting something? So I think, again, we can say mgh. I think we can say the time is going to be the mass, fairly heavy safe, times the acceleration, times the height, divided by 5 times 750. If we rev this motor full as hard as it can, what's the fastest we can lift this safe up? 39.2 seconds. Because this motor can exert a maximum of 5 horsepower, that's the fastest you can lift it up. And that's assuming this motor is 100% efficient. Are motors 100% efficient? Nope. There's a second way to think of power. This is one of those, John, handy to have in your back pocket kind of equations. Power, we said, is work over time. And we said that work is force times distance over time. Yes, Taylor? Look at those. What's distance measured in? Meters. What's time measured in? Hey, what is meters per second? You know what? Another way to think about power is force times average velocity. Mr. Duke? Yeah, Jake. When do you use that? When they start talking about power and I see no time in the question, but I can see a speed. I pull this one out of my back pocket. This one's not on your formula sheet, but Megan, did I kind of just show you how to kind of derive it in a pinch if you need to? Kind of pops out of there. I mentioned efficiency a little bit earlier. Efficiency basically asks how much bang do you get for your buck? The symbol for efficiency is, bear with me, got somebody at the door there. Keep going. Efficiency basically asks, of the amount of work or power or energy you're pouring in, how much do you get back? How much is useful? Did I give you an extra one? You got one? You got one? No? That was from last class? Oh, okay. Someone left it there. The symbol for efficiency, I didn't know this until I started teaching Physics 12, is the Greek letter eta, which basically looks like a lowercase n that droops. You know what? For years, I used as my abbreviation for efficiency. I don't care. I'll use the eta because, Gabby, I'm a nerd, and ooh, cool, I get to use Greek letters. I have to admit, my little math nerd heart loves using the Greek stuff. Efficiency, it's defined as how much work you got out divided by how much work you put in. Or how much power you got out divided by how much power you got in. or how much energy you got out divided by how much energy you put in. I have to be honest, I don't use any of those. You see, sometimes, Jason, I'll be doing a question, and in front of the amount of power that I'm getting out, the word in appears. Or in front of the amount that I'm putting in, for some reason the word out appears. Just grammar works that way sometimes, and it's a little confusing. In fact, I have a question in my mind that you're going to see on a test about 4 tests from now, where about 1 in 5 students does that. They calculate the efficiency, and because in terms of the output the word in appears, they assume, oh, that's that power in. When, if you think about it, it's not. You know what I know, Jake? You can't be more than 100% efficient. I live in the universe. So what I actually do is this. I know that efficiency is always the smaller number divided by the bigger number. Now, if you can create an efficiency that has the bigger number on top, and you are right, you will win the Nobel Prize. Not only will you win the Nobel Prize, they'll name units after you. Not only that, the list of scientists will no longer go Einstein, Newton, Archimedes. It'll go your name, then Einstein, then Newton, then Archimedes. If you can figure out free energy, you've solved almost every world problem. Because almost anything out there we can solve if we have unlimited energy. We can figure a way around it. But sadly, we're pretty sure that's impossible. We're pretty sure that nothing is more than 100% efficient. Oh, the fancy word for something that is 100% efficient is unity. So we say you get unity if you're 100% efficient. Now, it all depends on what you mean by efficient. Light bulbs, believe it or not, are 100% efficient. Sort of. A lot of the energy goes into heat, but if it's in your house, that heat doesn't vanish. That heat heats up your home. In fact, about a year ago, the government wanted to, and still has tried to, phase out incandescent bulbs and bring in fluorescent bulbs, and it's bad science. They mean well, but it's bad science because they're saying, well, the incandescent, the fluorescent light bulbs that when you screw them, that you can screw into a regular light socket, those ones, oh, they're more energy efficient. They're not more energy efficient. They are more electrically efficient. You use less electricity. But in my incandescent bulb, as long as it's in my house, any extra energy that doesn't go into light lowers my heating bill by exactly that much. So when I replace that incandescent bulb with a fluorescent one, my heating bill goes up. I don't come out ahead. It was some poorly thought out science when they did that. A light bulb is not 100% efficient if you're asking how much of it goes into light. Barely any. Most of it goes into heat. But a light bulb is 100% efficient if you're asking how much of it do I end up using. Okay, Gabby's looking at me and just saying, yeah, Mr. Dewick, but what about in the summer? In the summertime, you wouldn't want the heat. True enough. Gabby, we live in the northern hemisphere, yes? In the summertime, are our days fairly long? Do we use light bulbs more or less in the summertime? Much less. Much less. Really, the fluorescent ones, they make the most sense somewhere that's warm with shorter days, like around the tropics, fair enough. But it's not as good as people think. Oh, and the fluorescent ones have mercury in them. They're really a problem to dispose of. You're not supposed to just throw them in the garbage. You're supposed to take care of them properly. And mercury is scary. The LED bulbs are different, though. Those ones last a long time. Anyways, so efficiency is always less than 100% unless you plan on winning a Nobel Prize. A typical household light bulb transforms energy at a rate of 60 watts. 60-watt bulb. 60 watts, Jason, means 60 joules of energy every second. Most of the electrical energy, unfortunately, is transformed into heat instead of light. Approximately 57 watts of heat and 3 watts of light are produced by the lamp. An incandescent bulb is therefore only about 5% efficient. A kettle might transform electrical energy into heat at the rate of 1,500 watts. The power rating of an electrical appliance is usually printed somewhere on the appliance. You want to know how many watts an appliance is? You ask yourself, how much heat does it move around? The more heat it moves around, the higher its wattage. Kettle moves around a fair chunk of heat. Stove, very high watt. Microwaves, pretty high watts. Dryers, very high watts. Kitchen fans, not very high watts. Example 3. A 250 kilogram mass is lifted at a constant speed of 2 meters per second for a distance of 12.5 meters. A, find the work done. A. You know what? I'm going to be a little careful. I'm going to say the work is the change in potential plus the change in kinetic, because this one looks kind of scary. I'm going to fall back on the work energy theorem, which is the more comprehensive definition of work. But do you see the word in front of the word speed? What word is in front of the word speed? Constant. So what's your change in kinetic energy? 0. So you know what? I think I can hedge my bets and I can say that. And then I can say, oh, what's my initial potential energy, do you think? How high are we when we start? I think on the ground, yes. So you know what? I could have gone straight to work is force times distance, mgh. 250 times 9.8. By the way, you notice what I'm doing? If I can't bring Jaron to the front row, I'll bring the front row to Jaron. 12.5. Actually, I'm just trying to take advantage of this and get used to wandering around when I teach. I think it's less of a distraction. What do you get? 30,000, 30625? So 3.06 times 10 to the 4th, and this is work joules. B. B. Diana, what do they ask me to find in B? Power. Power, we just said, was work over time. Oh. Do you see a time anywhere in here, Diana? No. Ah. Oh, we also said that power was, since work was force times distance, we said, you know what? You could actually go force times average speed. Oh, that's why they said constant speed, because they want me to realize that the constant speed is the average speed because your speed's not changing. Aha! Nice try. Which force, by the way? Which force do you think? Oh, yeah, gravity. We're lifting. This is going to be mg. V, here's a new one. We haven't used this one before. M, 250. 9.8. V, 2. 4,900. Units? What? What? Ha 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 ha. C. If the motor is using 10 kilowatts, what's a kilo? Okay, so 10,000 watts. That's how much we're putting in. What's its efficiency? Efficiency is smaller number over the bigger number. Make sure the units match. 4,900 watts over 10,000 watts. And then times 100% to make it a percent. You know, I don't even need a calculator for this. I think it's going to be 49%, isn't it? Where'd the rest of the energy, where'd the rest of the power go? Sound, heat, other stuff. Now, electric motors, you'll learn later, are much more efficient, and they have a unique property. They're at their most efficient when you rev them the hardest. That's why electric cars, hybrid cars, that's why, because you may have wondered, hey, if a hybrid car still has a little gas generator in it, isn't the energy still coming from the gas? Why are they getting so much better gas mileage? Because they're using the generator to turn an electric motor, and an electric motor is way more efficient. Oh, any of you have a hybrid? You guys do? You drive one? Or you folks drive one? Or do you own one yourself? You do yourself? Wow, I'm impressed. When it's in electric mode, how loud is it? Oh, so you're not losing energy to sound? In fact, they are so silent, it's a problem, right? They've had to actually, for the hybrids, they add sound to them because they're worried that pedestrians who are trained to listen for a vehicle or people who are visually impaired won't be able to hear the vehicle coming. So they add a sound to it. Does it give off a lot of heat in electric mode? Have you ever tried putting your hand on the hood after you've driven for a while on a battery?
Pretty cool.
So yeah, much more efficient. Why, Mr. Dewick? Tune in May and find out. Oh, and when we look at electric motors, Terry will be giving everybody free rides. Example 4. Okay. A mass of 100 kilograms is pushed along the floor at a constant speed of 2 meters per second. If the coefficient of kinetic friction is 0.25, what's the power output? Do you see a time here anywhere? No? Ooh, Diana, do you see a constant speed again? I think they're going to want me to actually say that power is force times velocity. Mr. Dewick, they didn't mention a force. You know what? I think we better, because I see a coefficient of friction, I think we better free body diagram. Let's represent the mass with a dot. What are the forces acting on this mass? Get the obvious one. Gravity down. And we're on a floor, so I think we'll assume everything is level. We'll assume normal force is the same size as gravity. And then I guess we're pushing. We'll call this the applied force. What other force?
Friction.
Friction. How big? There's a key word that tells you exactly how big. It's the word in front of the word speed. Okay, if it's a constant speed, what's your acceleration? 0. So how big is friction compared to the applied force? They are?
Equal.
Yoink. So in my equation, I'm really going to be going the applied force times velocity. Oh, I don't know the applied force. Ah, but look. I know another force the same size as the applied force. What? Friction. Friction is what times what? See how we're putting everything together? By the way, I'm not going to say I like this question, I like this question, I like this one. I'm just going to say I like this question. Holy smokes, let's put together 2 units of good stuff in one question. This is good, covering everything. Sorry, what did you say friction was? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. What? So here we have it. Mu mg v. That's how much power this person must generate if they want to keep this object moving across the floor at a constant speed. Mu 0.25. 100. 9.8 times 2. Uh, 25 times 2 is 50. 5 times 40, 49, 490?
Yes.
Yeah. Units? What? Okay. Is that okay, Dorothy? Yeah? Okay. Example 5. A girl pushes a 300 Newton, oh, they gave me mg instead of mass. I'll make sure I notice they gave me newtons, yes. Box across the floor for a distance of 4 meters. Coefficient of kinetic friction is 0.33. She then lifts the box straight up. What's the minimum amount of work she's done? Okay, I think there's 2 situations here. I think there is pushing. I think there is lifting, and then we'll total them up. We'll total them up. Let's do the lifting first. Lifting, how much work do you do when lifting? I think that one we've done a bunch of times. When you're lifting, it's mgh. Now, she may have also sped it up when she lifted it, but it does say minimum amount of work, so I think it's assuming no change in kinetic energy, constant speed. It's going to be mass. Oh, no, not mass. mg is 300, so it's just going to be 300 times 1.2. This I can do in my head. That's going to be 360 joules. Because 3 times 12 is 36, so 300 times 1.2 is 360. What about the pushing? Now, again, it says, Ty, minimum amount of work, so I'm going to assume she's pushing at a constant speed. In fact, Ty, did you write down that free body diagram at the top of the page that we did for the previous question? Did you jot it down? Ty, did you write this down? That up there? You did? Yeah. I think it's the same diagram for this next question if we assume minimum. Okay? In other words, I think for pushing, I'm going to say work equals force times distance, and it's the applied force. I don't know the applied force. Oh, but look, 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 look. I know another force the same size as the applied force, friction. I think it's going to be force of friction times distance. Jaron is going to say friction is what times what mu times the normal force, Mr. Dewick. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. I think we're going to end up with this, mu mg d, where mu is 0.33. mg is 300. d is 4. Well, 300 times 4 is 1,200 times 0.33. 1,200 times 0.3 would be 360. It's going to be 360 plus 36. It's going to be 396? Yeah? Joules. What's the total amount of work done? Now, Jaron says 756. Wait a minute. Aren't you adding a horizontal and a vertical? Don't erase it. Don't erase it. Energy, vector or scalar? Scalar. Work, vector or scalar? Then who cares about the direction? We can add them up. We can add them just like normal math. No worrying about tip to tail. This is why energy is so nice, because if you have a change in direction, or especially, Megan, roller coasters that are all curvy, which really to analyze them vectorially would mean you'd have a constantly changing direction. Ugh. No, energy, scalar. Just cares about before and after. Doesn't care about what happened in between. Total is going to be 396 plus 360. The minimum amount of work, assuming she never increased or changed the speed of the object, she never gave it any extra kinetic energy, is 756, yeah? Units? Joules. Okay. Example 6 is your first actual Physics 12 question in this unit. You know how I can tell just by glancing at it that it's a Physics 12 question? Do you see it? Lawnmower, but what do you see in there? Angle. Angle. That's usually your clue this year. Hey, if there's angles, that's the difference between Physics 11 and Physics 12. Because actually, if you think about it, I haven't taught you a single new thing yet this year. You haven't learned a single new equation yet this year. You haven't learned a single new concept yet this year. All I'm saying, Sydney, is, hey, let's get a little better at vectors, and here's how we handle it. So I think we may do a free body diagram here. Let's read the question. It says, a person pulls on a lawnmower with a force of blah, 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 and moves the mower 4.5 meters. The handle angle is 15 degrees with the horizontal, and mu equals 0.1. Find A, the work done by the person, B, work done by friction, C, the time. This is going to be a pretty challenging question, especially part C, but that's okay. I think I'm going to do a free body diagram. So there's the lawnmower. What are the forces acting on it? Get the obvious ones. Good old mg down. Yoink. What else? Normal force. Now careful. How are we tackling this lawnmower? Are we lifting up or are we pushing down? What does it say? Pulls or pushes? Pulls. So if I pull, what happens to the normal force if I pull? Gets bigger, gets smaller, or stays the same? Gets smaller. That cost a lot of you marks on your test, by the way. Hint, hint, wink, wink, nudge, nudge. I'm going to draw a shorter normal force. Yoink. Like that. A shorter normal force. What else? Well, there's the applied force, the person pulling up. Yoink. And how big was that? 25. What else? Oh, there must be friction. There is my free body diagram. There's a list of all the forces. Oh, and of course, we would then say we're going to break this angled one up into horizontal and vertical, right? All right, let's see if we can tackle this. John, what's A asking me to find? Work done by, sorry?
The person. Or person.
Okay. Work is going to be force times distance. I see they did give me a distance, yes? Now, careful. Which force am I going to use if I want to calculate the work done by the person? Mabad. Fx, not the 25. I have to use the horizontal. Why? Because the distance is horizontal. This is where direction does matter, right? So it's actually going to be Fx times d. What is Fx? Adjacent, hypotenuse. What? You know what? It's going to be 25 cos 15 times, what's the distance? I've scrolled over. 4.5? How much work was done by the person on the object? Sorry, how much work was done by the person, not on the object, but how much work was done by the person? What do you get? I think you get like a 108.66 or something like that. Okay. 108.66, which to 2 or 3 sig figs is 109 joules. All right, let's keep going. This is kind of nerdly cool. B, find the work done by what? I guess the work done by friction is going to be friction times distance. And why am I technically wrong here? Something very subtle. Which way is this lawnmower moving? To the right in my diagram? Yes? Which way is friction acting? So you're saying that the force is in the opposite direction of the distance? But a negative. We're losing energy to friction. We're losing energy to... Okay. Jaron, friction is what times what? No, friction is what times what? I don't know the normal force. Oh, but look, ooh. I was going to say, look, 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 look. I know another force the same size as the normal force. Really, I don't exactly. I know over here that, let's see. You know what? I didn't even put the Fn on there. Let's put it on there. I know that the normal force plus Fy cancels out gravity. Right? So I know that the normal force is gravity minus Fy, Fn, Mr. Duke, minus Fy. What is Fy in terms of that 25? What is Fy? Sine, okay. So this is going to end up being, what was the mass? I've scrolled down. What was the mass? 20 times 9.8 minus 25 sine 15. And I'll carry this to a few extra decimals because I'm going to be using it. 20 times 9.8 minus 25 sine 15. I get a normal force of 1.8953. I'll use that. 189.53. So, back up here. What was mu? Negative, what was mu? 0.1 times the normal force, 189.53, times the distance, which was 4.5. Conveniently, I still have that 189.53 stored on my calculator, so I'm going to go that times negative 0.1 times 4.5, and I get negative 85.3 joules. I lose that much energy. Are we right? Negative 85.3 joules. Friction takes that much energy out. So this person is pouring 109 joules of energy in. Friction is taking 85.3 joules of energy out. That only leaves, what, about 24 joules of energy left over that goes into speeding up this lawnmower. This lawnmower will be gaining kinetic energy, which means it will be speeding up, but not as fast as it would be on ice, say. What's C asking us to find? Sorry? Time. Yeah. Well, I think we'll assume that V initial is 0. We know distance, 4.5. I think if I can find the acceleration, I can find time. Or I could try finding V final and find time, but to find V final, I think I'd need the acceleration anyhow. So no matter what, I think my first goal is to find the acceleration. Okay. Hey, look at your original diagram. Who's winning? Who's winning? FX. Who's losing? We could go winner minus loser equals MA. We could say that the acceleration is Fx, that was 25 cos minus mu times the normal force, which was 189.53, all divided by, what was the mass? What was the mass, Mr. Dewick? 20. And I could say, well, I'm accelerating at, bracket, 25 cos 15 minus 0.1 times 189.53 divided by 20. I'm accelerating at 0.2598 meters per second squared, and I can put that there. And now I'm looking for an equation that has d, a, vi, and t in it. Looking for an equation that has d, vi, a, and t in it. There is one. Which one, Gabby?
This is equal
You are correct. D equals VIT plus a half AT squared. Is VI 0? So in your mind, cross that out. Can you get the T by itself?
time equals 2D.
Megan, what is it? You were whispering it right, I think. Like I just wrote there? Yeah. Yep. Okay. Now, I think this question in terms of the amount of work is a little overkill. I do say, Sydney, I like this because this really is a review of all 3 units in one question. Look at that. Did we do winner minus loser with angles? We did. Did we just bring in some kinematics from Physics 11 and Unit 1? We did. Oh, and did we also do some work? No pun intended. Yeah, we did. I mean, I kind of like that. That's why this is a nice question. And it's something very simple. Pushing a lawnmower. Something most of you have done. Is your lawnmower electric? You know they make those robotic ones, right? Solar powered? I had one of those Roomba vacuums for a couple of years. It was very cool. 4.5 divided by 0.2598. You get 5.9 seconds? Woohoo! Now here's my question for you to think about. Could I find that time using energies, work, power, and time? Because power is work over time. I think if they'd given me, did they give you a constant speed in this question? No. See, I think if they'd given me a constant speed, I could have said power equals power, force times velocity equals work over time. And then I think I probably could have, because I know how much work, I could have figured out the force and the velocity. It works some magic. No big whoop. Turn the page. Oh, too far. Example 7. Another lawnmower. Woohoo! Oh, this time they push on the lawnmower. Okay. So I think this time my free body diagram, which I am going to do because this has got an angle, is going to look like this. What are the forces acting on it? Get the obvious ones.
Gravity.
Darn right. Are we pulling up on the lawnmower or are we pushing down? So if I push down on my table, what's going to happen to the normal force? Same, increase, or decrease? I'm going to exaggerate that. Go, gadget, normal force. And I'm going to be really clever. I'm going to put the mg on that side so I can, you don't push down like that. Here's the applied force, which is 75 newtons. And there would be friction. So my free body would look like that. Oh, and then I would say components. Fx, Fy. Cool. What's A asking me to find? What's A asking me to find? The rate at which heat energy is generated. You know what? I think it's asking me to find how much power goes into heat, because the rate at which energy is generated, that's our definition of power. So power is going to be work over time where the work is going to be the work done by friction, because that's what generates heat. Okay. This is going to be the force of friction times the distance divided by the time. So far, so good. Friction is what times what? So this is going to be mu times the normal force times distance divided by time. I don't know the normal force. Oh, but look, ooh. How big is the normal force? Can you give me an equation from this diagram? Taylor. Louder, you're right. Which I think is going to be mg plus 75 sine of, what's the angle? 20? The normal force is going to be m 25, 9.8 plus 75 sine 20. How big is the normal force here? It's going to be 25 times 9.8 plus 75 sine 20. I get a normal force of 84.436. I'll carry a few. I missed a plus sign, no kidding. I get a normal force of 270.65. Is that better? 25 times 9.8 plus 75. Yeah, yes, no? Yeah. So you got? Josh, you got that? Oh, you were looking like 270.65. I'll keep a few extra sig figs because that's not my final answer. And I'll go trucking up here. Mu. .21 times the normal force times the distance, 30, over the oh. Did they give me the time? No. Oh, did we figure out time in the last question? Okay. Here we go. I guess we can say this for time. You know what? I'll do, I think I can do time over here on the left. I got room. For time, I can say t equals, I don't know. They did tell me we start at rest, yes? And I know the distance is, how far are we traveling? 30? I think if I can find that, we're good to go. I can find t. In fact, it's going to be the same thing we just did. Megan's bursting to say time is going to be 2 times d divided by a square root of that whole thing. Yes, she is right. How am I going to find a? Winner minus loser. Who's winning? Fx. Who's losing? Friction. That equals ma. The acceleration is going to be Fx 75 cos 20 minus friction. 0.21 was mu? What was mu? 0.21? Mu times the normal force, which was 270.65. If I divide that by the mass, 25, that should give me the acceleration. (75 cos 20) bonk, minus 0.21 times 270.65, close bracket, divided by 25 to get an acceleration of 0.5456. Woohoo! Now I stick that there, and I can get t equals the square root of 2d over a. 2 times, what was d? 30? Divided by my last answer, haha. Square root of that. I get a lovely time of 10.49 seconds. And now, plug that in for there. Please tell me we get the right answer for power. How many watts of energy do we give away to heat? Sorry, how many watts of power do we give away to heat? You okay there, Megan? Okay. Sorry, how much? 163? What's the answer say? You know what? We're to 2 sig figs, and our third one's really close. It's rounding along the way. Units, Ty?
Joules per second.
Or we can call that what?
Watts.
What?
Watts.
What? Yeah. B says find V final. We could pretty easily now. I got A, I got T, VI is 0. I'm not going to waste my time on it. Okay. What's your homework? We're not going to do the last question. Okay. Number 1, 2, 3, 4 is good. 6 is good. I skipped 5. 7 is good. 'So far I've gone 1, 2, 3, 4, 5, 6, 7, skip 5. So 1 through 7, skip 5. And I'm going to stop there. I have a take-home quiz. And also your homework is you can now do every question on the review. So your test is a week on Friday, and the review is due there. Yes, you may. Hustle back. And then I got some nerdily cool videos to show you too.